So welcome to this class on Laplace transform. I think that if you all are quite aware of Laplace transform, then we can proceed towards the topic that solving differential equations by using Laplace transform. Are you all aware of the topic Laplace transform? Or I proceed initially what is Laplace transform, how Laplace transformations are done, what are the Laplace transformations of different common functions, or then I will proceed to solve the differential equations. Please suggest me on the comment box that what I have to do. Yes, good evening to you all. Just comment that whether I am going to start the topic from solving the differential equations, that is different functions and how different functions can be Laplace transformed. That is all known to you, or I will proceed from the very beginning of the topic, that is how to transform different functions by using Laplace transformation. Okay, Pranav has already answered that start from initial. Anyone? Please start from very beginning. Okay. So let's start from the very beginning of the topic, that is the Laplace transformations. Now, as the topic tells the name, that is Laplace transformation. So, this is a transformation equation, or rather by using this particular topic, that is Laplace transformation, we can transform any function from one definite part to another definite part, that is one definite function to another definite function. Now, wherefrom we can transform one function to another. We can transform any function from its time domain. We can transform any function from its time domain to its frequency domain, or vice versa. So Laplace transformation actually enables us to transform a function which is defined in its time domain to convert it or to transform it into its frequency domain. And when we have applied the inverse Laplace transform, that is, then we can transform a function from its frequency domain to its time domain. So this is a transformation equation which can transform any function from a time domain, from its time domain to its frequency domain, or vice versa. Now, how it can be done? Let us define a function f of t. So a function f of t, as you can already know, or you can read it as a function which is defined in its time domain, and this function can be converted to its frequency domain. Now that S is actually the frequency domain, so ft can be converted to fs by using the Laplace transformation, or you can convert this frequency domain function to its time domain function by using the inverse Laplace function. So this is the inverse Laplace, this is the Laplace, and the symbol enables that it is just a capital L in cursive manner. So I have already written today's topic in this cursive form just to give you a visualization that this is nothing but the cursive form of capital L. So cursive form of capital L tells us that it is the Laplace transformation, and inverse Laplace, that is L to the power minus 1, is the inverse Laplace, and this inverse Laplace also enables us to give the function to its from its frequency domain to convert it into the time domain. Now how it can be done? It can be done by using Laplace transform of f of t, Laplace transform of f of t, which actually gives us capital F of s. You can find this value. You can find it by using this integral 0 to infinity f of t and then e to the power minus of st dt. So this is the form. Now we are considering only the Laplace transformation. Initially we have to consider initially the Laplace transformation. So the Laplace transformation of any function which is given in its time domain form, it can be converted into the frequency domain form, and the integral value of the integral form is nothing but integral 0 to infinity f of t e to the power minus st dt. So first of all, that functional form of f of t should be given to us. It is given in the problem, and then you have to proceed. You have to go through this integration, and then you can find the value, whichever is the value. This is nothing but the Laplace transform of f of t, and it can be written as capital F of x. So this is the one line equation. This is the simple equation which can convert any function from its time domain form to its frequency domain form. I think all you can understand this up to this. Is it? Is it okay? Okay. So now let us take some examples. Let us solve or rather let us convert some function from the time domain form to its frequency domain value. Let's take number 1. Say this is our number 1 case where f of t is a constant. Say it is given as 1. F of t equals to 1. So Laplace transform of f of t by using this formula, that is capital F of s, it will be integral 0 to infinity. Now putting the value of f of t, that is here for this case is 1, and then e to the power minus of st dt. Always we have to go through this particular integration, and then the value is integral of 0 to infinity e to the power minus of st dt. Now e to the power x, integral e to the power mx means the value is e to the power mx by m. So since this is a definite integral, we have to put e to the power minus st by minus of s, and the limit is 0 to infinity. So it will be minus 1 by s e to the power minus of infinity minus e to the power 0. It will give minus 1 by s. E to the power minus of infinity means 1 by e to the power infinity. E to the power infinity is only infinity, so 1 by e to the power infinity equals to 1 by infinity, and that will be equals to 0. So the value of e to the power minus infinity is 0. So putting this value as 0, minus e to the power 0 is 1. So the value is nothing but 1 by s. As you can see, the function has been given in the time domain, and then after using the transformation, we have converted the function into its frequency domain. So that is the essence, that is the usefulness of Laplace transformation. Is it okay? Is it okay? Now take another example, that is number 2. Let f of t that equals to t. So Laplace transform of f of t, that is Laplace transform of simply t that equals to integral 0 to infinity t e to the power minus of st dt. Again by using the same formula, that is integral 0 to infinity f of t then e to the power minus st dt. So this is nothing but by putting the value of f of t as given by t. So this will be integral 0 to infinity t e to the power minus st dt. Now to perform this integration, we must go through the integration by parts form. So taking t as the first function and e to the power function as the last function, or rather the second function, we have to use, that is given first function integral of the second, that is e to the power minus st by minus s limit 0 to infinity minus integral differentiation of the first, that is 1. By differentiating t we have 1, and then integral of the second, that is e to the power minus st by minus s dt. So it will be t, or rather minus 1 by s e to the power of minus st minus integral 0 to infinity minus minus plus 1 by s e to the power minus of st dt. Let's omit this problem number 1 and then simplifying we have, so putting the value of the limit, that is 0 to infinity, so it will give us 0, so we are left with 1 by s. Now e to the power minus st, integral e to the power minus st means e to the power minus st by minus of s limit 0 to infinity, so it will give minus 1 by s square, and then putting the value e to the power minus infinity minus e to the power 0, that is 1, so e to the power minus infinity, again it will give nothing but 0, so it is, the value will be 1 by s square. The value is 1 by s square. Okay, so this is the transformation of function on f of t equals to simply t, that is the value 1 by s square. Is it okay? Is it okay? Okay, so let's move on to derive or take example number 3 or function number 3, and this is an exponential function. When f of t, if f of t is given by problem or functional form number 3 e to the power say alpha t. So here the function is given as e to the power alpha t or e to the power at, whatever may be. So we have to again deduce the Laplace transform of f of t, that is the Laplace transform of e to the power a or e to the power alpha t. Then again it will be integral 0 to infinity the value of f of t, that is e to the power alpha t e to the power minus of st dt. Okay, so we have 0 to infinity e to the power minus of s minus alpha t dt. Fine. So the integral form will be e to the power minus s minus alpha into t divided by minus of s minus alpha, where the limit is 0 to infinity. So we have minus s minus alpha 1 by s minus alpha e to the power minus of infinity minus of e to the power 0, that will be minus 1 by s minus alpha. It is 0 minus 1, so the value will be 1 by s minus alpha or 1 by s minus a. So if the function every time while we have to proceed or we have to solve the differential equations by using the Laplace transformation, we can't deduce these equations right now, or rather we can't deduce these equations every time we have to use. So these particular functional forms, should be remembered, and that's then while we have to derive or we have to solve the differential equations, we will just put these particular values and then we can proceed through the topic. So we have to know the various transformations, or rather the transformations of various or rather different functional forms. So this is an important function, e to the power alpha t. So the functional or the Laplace transform of e to the power at or e to the power alpha t is nothing but 1 by s minus alpha. Okay? Is it okay? Okay, Dipanjan. So up to this we have already transformed, or rather we have already used the Laplace transformation to transform three different functions: f of t equals to 1, f of t equals to t, and then f of t equals to e to the power alpha t. Let's take the fourth form, and it is quite similar to this particular value, and that is nothing but f of t equals to e to the power minus of alpha t. As we know that this is an important functional form, that is e to the power of minus of at or e to the power minus of alpha t. So by proceeding similar manner, we can write, that is integral 0 to infinity e to the power minus of alpha t into e to the power minus of st dt. So now taking minus common, we have alpha plus s, or rather we can write s plus alpha into t dt. You just careful that every time while taking the common, while we have two exponential terms in this Laplace transformation form, every time take common and take this s at the first term. Take s as the first term, so we have e to the power minus of s plus alpha t dt. So after doing the integral, again the similar value will have, that is e to the power minus of s plus alpha divided by minus of s plus alpha, and the limit is 0 to infinity. So it will be minus of s plus alpha, and then e to the power infinity means 0 minus e to the power 0, that is 1. So we have the value 1 by s plus alpha. So what we have in our hands, that is while taking that functional form as e to the power of alpha t, we have the frequency domain form as f of s equals to 1 by s minus alpha, and while the functional form e to the power minus of alpha t, then functional form in the frequency domain, it is 1 by s plus alpha. So while the function has a form of e to the power alpha t, e to the power alpha t or e to the power at or e to the power bt, the frequency domain form is e to the power 1 by s minus alpha or 1 by s minus a or 1 by s minus b. That is a constant term, alpha, a, b, whatever may be, but the form is 1 by s minus. 1 by s minus while the function in the time domain is in positive part. Again, if the function in its time domain form is e to the power minus of alpha t, that is negative part, e to the power minus of alpha t, then the frequency domain form is 1 by s plus alpha. So remember this part, that if the function has a negative value, then the frequency domain form is a positive one, and if the function has a positive value, then the frequency domain form has a negative value. So this way you can remember these functional forms of 3 and 4, and these are nothing but the exponential forms, either e to the power alpha t or e to the power minus of alpha t. Okay? Today I am a bit speedy. Is it problem for you to cope up with my speed, or I will decelerate, or is it okay? Is it okay? Have you all cope up with my speed? Today I am a bit fast. So, Shobik, okay, Pranav, okay, no problem, fine, thank you. So let's move on to derive some more functional forms, and always remember these transformations, you have to remember the values of these particular transformations of these simple functions. So let's move on to derive f of t equals to cos hyperbolic omega t. So this is the form, or we can go through f of t equals to sine hyperbolic omega t. Right. So these are the functional forms. These are also, as you know, these are also very important functional forms. Every time we find these particular forms, we can find these particular forms in our physics problems or in our equations which are used in physics. So these are the forms: cos hyperbolic function, sine hyperbolic function. They are very much important. So we have to go through to find their transformations. Now for this to happen, we initially, or rather at first we must proceed towards a property of Laplace transformation, and that is the transformation of linear combination. So that is known as the transformation of linear combination. Now this property tells us that if f1t and f2t, are two functions of time, as we can see, where f1t, and if a and b are two constants, then the Laplace transform of a into f1t plus b into f2t. So what will be the value of this particular combination, that is where a into f1t, a is a constant, and then b into f2t, where again b is a constant? We can write it as a into Laplace transform of f1t A into Laplace transform of f1t plus B into Laplace transform of f2t. So if you have the values, if you know the values of f1t, that is the Laplace transform of f1t and the Laplace transform of f2t, so you can just put these values and then you can find easily the linear combination of the Laplace transform of A f1t plus B f2t. So this is a simple method, or this is a simple property to be used to derive these particular functional forms, that is cos hyperbolic omega t or sine hyperbolic omega t. As we know, why? As we know that cos hyperbolic omega t, what is the functional form or what is the value, how we can expand this? Cos hyperbolic omega t is nothing but half e to the power omega t plus e to the power minus of omega t. So this is the value. This is the expanded value of cos hyperbolic omega t. Now to convert Laplace transform of cos hyperbolic omega t, you can find it that we can write it as Laplace transform of half e to the power omega t plus e to the power minus of omega t, right? So it can be written as Laplace transform of half e to the power omega t plus half e to the power minus of omega t, and that you can compare with this particular value or particular form, that is Laplace transform of A into f1t plus Laplace transform of any constant B into f2t, and here we also have the form of Laplace transform of A, here half f1t, rather e to the power omega t plus half f2t, that is half e to the power minus omega t, and already we have known the particular transformations of e to the power omega t or e to the power minus of omega t. Just now we have find their values, so we can write it as half Laplace transform of e to the power omega t plus half Laplace transform of e to the power minus of omega t. Now just by putting their values, Laplace transform of e to the power alpha t, we have just now derived this, we have find their values, that Laplace transform of e to the power omega t should be 1 by s minus omega. E to the power minus of omega t, the transformation of e to the power minus of omega t is 1 by s plus omega. So just now put these values, that is we have Laplace transform of cos hyperbolic omega t, that equals to half of e to the power, Laplace transform of e to the power omega t means 1 by s minus omega, then plus, or we can take half as common, plus 1 by e to the power 1 by s plus omega. So these are the values right now we have derived. So now you can simplify this further, that is it will have s square minus omega square, so s plus omega plus s minus omega, so it will be twice s, cancelling 2 here, we have s by s square minus omega square, s square minus omega square, and that is the value of Laplace transformation of cos hyperbolic omega t. So the transformation of cos hyperbolic omega t or the Laplace transformation of cos hyperbolic omega t is given by s square minus omega square. Is it okay? So to derive this Laplace transform of cos hyperbolic omega t, we have used this expansion of cos hyperbolic omega t, and then applying this particular property of Laplace transformation of combination of two functions, and just now we put their Laplace transformation values, and simply we have obtained, or we obtain the particular value. So Kaji Manwar, Manwarul Islam, you are asking that negative এ কি inverse হবে, negative এ কি inverse হবে? I don't get it. Negative, if the value is transformation of e to the power at, if the transformation of the time domain function is e to the power at, then the transformation that is in frequency domain, it will be 1 by s minus a, 1 by s minus a, and if the time domain function has e to the power minus of at, then the value will be 1 by s plus a. Momita asked me where from the s comes. Just simplify these two and you will have in the numerator part s plus omega, then plus s minus omega. I have already skipped this part, but if you have any problem, you can find out this value, that the denominator has got a value of s square minus omega square, and then in the numerator part you will have s plus omega plus s minus omega. So the omega cancels each other, and then you have twice of s in the numerator part, and then cancelling 2, you have s by s square minus of omega square. Is it okay? No sir, বুঝতে পারলাম। Manwarul Islam, have you any problem? Or rather it is okay? Is it okay? Manwarul, is it okay? I'm waiting for your response. So Momita, okay. Amor Pal, okay. Okay, so Manwarul, it is okay, so let's move forward. Okay, now let's take this function, that is f of t, if the function has got a value of sine hyperbolic omega t. So the difference between the cos hyperbolic function and the sine hyperbolic function, that in their expanded form, as we can write cos hyperbolic omega t equals to half of e to the power omega t plus e to the power minus omega t. The sine hyperbolic function can be written as half e to the power omega t minus e to the power minus of omega t. So sine hyperbolic function can be written as half e to the power omega t minus e to the power minus of omega t. So proceeding in this similar fashion, we can write Laplace transform of sine hyperbolic omega t. Laplace transform of sine hyperbolic omega t can be written as, or the value should be, I am skipping some steps as I have shown here. So the Laplace transform of sine hyperbolic omega t can be found as half of Laplace transform of e to the power omega t, then minus of half of, or rather you can take half common, so you can write as Laplace transform of e to the power minus of omega t. Is it okay? We have expanded sine hyperbolic omega t. This is the actual form, that is sine hyperbolic omega t can be written as half of e to the power omega t minus of e to the power minus of omega t. So the Laplace transformation should be, or rather you can write it as by using the linear combination property, and as we have the values, we can put these values here, that is 1 by s minus omega minus 1 by s plus omega. So simplifying this, you have s square minus omega square, and then in the numerator part we have s plus omega minus s plus omega, and then this omega, or rather sorry, this s cancel with each other, we have twice omega by half, so it is omega by s square minus of omega square. So just don't get confused, as because the Laplace transform of cos hyperbolic, the Laplace transform of cos hyperbolic omega t is s by s square minus omega square, and the Laplace transform of sine hyperbolic omega t, the forms look similar but the numerator part is different, that is omega by s square minus omega square. So the Laplace transform of sine hyperbolic omega t is omega by s square minus omega square, where the functional or the transformation value of Laplace transform of e to the cos hyperbolic omega t is s by s square minus of omega square. Okay? So two functions cos hyperbolic and sine hyperbolic omega t, or rather two functions, two hyperbolic functions and their Laplace transformations are derived. Now let's move on to derive another two very important functions, that is simply the cos functions and the sine functional form. So I think it will be number 7. It will be number 7, where f of t equals to cos omega t, and number 8 it will be f of t equals to sine omega t. So now to trigonometric functions sine omega t and cos omega t, and we have to find out their Laplace transformations. Right. Now again we have to write these cosine functions, rather the cos functions or the sine functions, in their expanded form. And we have cos omega t. We can write it as half of e to the power j omega t. E to the power j omega t, what is the expansion of e to the power j omega t? That is cos omega t plus j sine omega t. Cos omega t plus j sine omega t. So e to the power j omega t plus e to the power minus j omega t. What is e to the power j omega t? Cos omega t, if you have forgotten the value, cos omega t plus j sine of omega t, and e to the power minus of j omega t, it is cos omega t minus of j sine omega t. So these are the values of e to the power j omega t or e to the power j theta. So now so e to the power j omega t plus e to the power minus of j omega t. So if you add these two, you will have cos omega t plus cos omega t, that is twice cos omega t. So divided by 2, you will have simply cos omega t. So here again, by using this expanded form of cos omega t, we have written these values. So by using again the Laplace transformation of the property of linear combinations, we can write this as half of Laplace transformation of e to the power j omega t plus half of Laplace transform of e to the power minus of j omega t. And as we all familiar with the Laplace transformation of e to the power j omega t, or rather e to the power alpha t, Here alpha actually is j omega. So by using that value, that is half into 1 by s minus alpha, that is s minus of j omega, right? 1 by s minus of j omega plus 1 by, again the Laplace transformation of e to the power minus at is 1 by s plus a. So here 1 by s plus a means j omega, so that is s plus j omega. Is it right? Okay. Shushmita, sir, how j comes? J comes from the de Moivre's theorem, and j is nothing but the complex number what in our earlier days we have written it as I. So j is there, j is that particular value, that is the complex quantity. It is nothing but equals to I. So this is the value of j, and by using the de Moivre's theorem we can write as e to the power j theta. This is the actual form of de Moivre's theorem. E to the power j theta equals to cos theta plus j sin theta. Cos theta plus j sin theta, I have written it as e to the power j omega t, and we have cos omega t plus j sin omega t. Is it okay? So now again simplifying this, we have s square minus of j square omega square. As j is complex, we have s square plus of omega square, and in the numerator part it will s plus j omega plus s minus of j omega. So j omega cancels, and we have s by s square plus omega square. So the Laplace transform of cos omega t. So the Laplace transform of cos omega t is equals to s by s square plus omega square, right? These all functional forms, you have to remember these all functional forms. So you have to simplify, or you have to find out these particular values by your own. Okay, or rather you can't remember these all functional forms, these all transformation forms, and if you forget these values, if you forget these functional forms, then you can't go through solve the differential equations by using Laplace transformation. Pranav, is it okay? Arindam, Uday, Masur, Haradan. So up to this, okay. So after find out the value of cos omega t, we have to go forward to find out the value of sin omega t. And sin omega t, as I have written the exponential values, that is e to the power j omega t, e to the power minus of j omega t. So to find out the values of sin omega t, what will be the form? The form will be e to the power j omega t minus of e to the power minus j omega t. So just minus e to the power j omega t minus of e to the power minus j omega t. So e to the power j omega t minus of e to the power minus of j omega t. What will you get? You will get cos omega t plus j sin omega t minus of cos omega t. So cos omega t cancels, plus of j sin omega t. So you have twice j sin omega t. Twice j sin omega t, but we have to find out the simple value of sin omega t. We have twice j sin omega t, so just dividing by this, that is 1 by 2j. 1 by 2j, we have simply sin of omega t. So So by putting, you need not to memorize this value. If you can't, then you just remember these particular forms. These are simpler forms. So that is 1 by 2j e to the power j omega t minus of e to the power minus j omega t, and that is the value of sine omega t. So sine omega t can be written as 1 by 2j e to the power j omega t minus of e to the power minus j omega t. So the Laplace transform can be found as 1 by 2j Laplace transform of e to the power j omega t. I have taken 1 by 2j outside, and then Laplace transform of e to the power minus of j omega t. Okay, so that will be 1 by 2j Laplace transform of e to the power j omega t is 1 by s minus of j omega minus 1 by s plus j omega. So by simplifying, we have s square plus omega square, and then s plus j omega minus s plus of j omega. So s cancels with each other. We have twice j omega divided by twice j, so that will give us omega by s square plus omega square. S square plus omega, omega by s square plus omega square, right? Is it okay? Okay. So now let's find out some other values. I think we can remove this also. So now number 9 and number 10. So we have came across and find out 8 different functional values, Laplace transform of 8 different functional values, and as you say, you have no problem right now. Now let's proceed some complex forms, and let the function f of t equals to e to the power minus of at into f of t. Let the function be e to the power minus at, e to the power minus at into ft. So here, as you can find, that we have two functional values, and this ft can be of any type. It can be a trigonometric function, that is sine, cos. It can be a hyperbolic function, cos hyperbolic, sine hyperbolic. So, or it can be any exponential forms. So if these particular forms, that is product of two functions, two different functions, is given in the value of f of t, what we can do? We can simply by again proceeding going through the definition of the Laplace transformation. So the Laplace transformation of e to the power minus at into f of t. Now where from these functions you can find these functions as exponentially damped function. It can be treated as physically as exponentially damped function as because the presence of this exponential minus e to the power minus term. So this can be physically treated as an exponentially damped function. Now by proceeding in the similar manner or by following the definition, we can write it as 0 to integral 0 to infinity f of t e to the power minus of at into e to the power minus of st dt. So this is the new function value, and then e to the power minus of st dt. So we can write it as integral 0 to infinity f of t and then e to the power minus s plus a into t into dt. So it can be written as this. Now from the definition of Laplace transform, that is what we have written earlier, that Laplace transform of f of t can be written as integral 0 to infinity f of t e to the power minus st dt, and that t can be written as capital F of s. Okay. Why I have written this again? I have written this to compare these particular forms. Just have a careful look. Compare these two particular values. What you find this is f of t, this is f of t, this is e to the power minus s plus a, and a is a constant, so that is e to the power minus of s plus a t dt, and this is e to the power minus of st dt, and that can be written as f of s. That can be written as f of s. If this form can be written as f of s, so what will we can write from this particular value, this particular form? Any idea? What can we write from this particular value, that is capital F of what will be the value? If this particular form can be written as capital F of s, then this equation can be written as just a simple answer. I am expecting from you just a simple answer. What can we write from this particular form? Again, I am asking that if this equation can be written as capital F of s, then what will be the value of this particular form? I want to write it as capital F of exactly Pranav, exactly Manwarul, Jayanto, very nice. You all are correct. So this can be written as, okay, Dipanjan, very nice. So this can be written as capital F of, fine Uday, this can be written as capital F of s plus a. So this is an exciting scene for me also, that okay. So up to this all you have understand. So that is a very so that can be written. So this equation can be written as capital F of s plus a, as all you were suggested. So Haradhan, okay, right? So fine. Now just take some examples. Remember this particular form. And now take some examples as Laplace transform of, if the function is e to the power minus at cos of omega t. So if the transformation or if the time domain function has a value of e to the power minus at cos of omega t, okay, so we have to put as, and we have the value as s by s square plus omega square. We have the value of cos omega t. So you have to find out the value of this frequency domain functional value. Frequency domain, that is capital F of s. Now what is s here? What is the value here? So the value here is cos omega t. Cos omega t, and if we write it as by expanding this, we can write it as integral 0 to infinity e to the cos omega t, and then e to the power minus at e to the power minus st dt. So this can be written as 0 to infinity cos of omega t, and then e to the power minus of s plus a t dt. So this is the time domain function ft, what we have already done. This is actually cos omega t form, and that is e to the power, sir please explain, e to the power minus st from this or from that. Imtiaz, second line means this. I am pointing out, I have written e to the power minus st here also, e to the power minus st here also. So where is your problem? Where is your problem? E to the power minus st, Imtiaz. It is nothing but the expanded value. It is nothing but, if the problem is here, it is nothing but this is the time domain function. This is the time domain function, and for the transformation to happen, to make the Laplace transformation, every time we have to use the formula integral 0 to infinity f of t e to the power minus st dt. Integral 0 to infinity f of t e to the power minus of st dt. So that is the value I have written here. This is the f of t value, and then e to the power minus of st dt. Okay. Now we can find out we have already find out the Laplace transform of cos omega t. Laplace transform of cos omega t, and we have the value of s by s square plus omega square. S by s square plus omega square. So now we have to write it as f of s plus a, f of s plus a, and this is nothing but the value should be s plus a divided by s plus a whole square plus omega square. Have you got it? So the value will be s plus a divided by s plus a whole square plus omega square. Why? The value of Laplace transform of cos omega t, what we have right now done, that is Laplace transform of cos omega t, that is capital F of s. Capital F of s is equals to s by s square plus omega square. So we have substituted the value of s as s plus a. The value of s as s plus a, as because this is e to the power minus of s plus a t dt. So we have to substitute as the Laplace transform of cos omega t equals to s by s square plus omega square, as the value of Laplace transform of cos omega t equals to s by it is the s by s square plus omega square. So we have to substitute s by s plus a to get the Laplace transform of f of s plus a, or e to the power minus at cos omega t, and then we have the value s plus a. So substituting s by s plus a, and we have s plus a divided by s plus a whole square plus omega square. Is it okay? Is it okay? So in this 1 hour of lecture, you all have understand what is Laplace transformation, right? So now if the function has a value of e to the power minus at sine omega t, if the value is minus e to the power minus at sine omega t, we have as the Laplace transform of sine omega t, as the Laplace transform of sine omega t is omega by s square plus omega square. So what will be the value? What will be the value? That is our number 10. So number 10 is, so now take the function as number 10 f of t equals to e to the power minus of at sine of omega t. Okay, so Laplace transform of e to the power minus at sine omega t. So you have to consider the this value as the original functional value. This value as the original function. Okay. Now, if this is the original function, the transformation value is given or is known to you that it is equals to omega by s square plus omega square. Just carefully listen to this part. You have to consider e to the power, not the e to the power term, but the rest part as the original function. Just consider here for instance sine omega t as the original function, and all you have known that sine omega t or the transformation of sine omega t is omega by s square plus omega square. Okay, Jayanto, have you given the answer that is omega plus a? No, Jayanto, this is not the value. This is not the value. This is not the value, as because we have to substitute s. Remember, we have to substitute s by s plus a. Janto, s by s plus a. So omega will be there. Omega will be there unaltered, and only the s value will be changed. Okay, so the functional or the Laplace transform of e to the power minus at sine omega t should be, that is omega, as because the functional value or the transformation of sine omega t was omega by s square plus omega square. So right now we have to write as s by s plus a. Yes, Momita, that is the right answer. That is s square. So s plus a square plus omega square. So this will be the value of e to the power minus at into sine at or sine omega t. Sine omega t. So the value is omega by s plus a whole square plus omega square. That is very nice. So you are using the properties. You have known how to use the properties, and you have correctly find out the values of these Laplace transformation forms. That is excellent of it. Okay. So already we have crossed the 1 hour mark, and I think I should stop here, and just in our next class we will proceed, we will apply these 10 functional forms or these 10 conversion formulas in to derive or to find out how to solve the differential equations by using Laplace transform. How to solve differential equations by using Laplace transform. Though today I have made the topic as solving of differential equations by Laplace transform, so that is not to be worried about. So we have already came across how to find out the Laplace transformation of different mathematical forms, and in our next class we will apply these particular forms. In our next class we should not find out the particular values of these particular functions, and we should use these functional forms to solve the differential equations by using Laplace transformation. So thank you, goodbye.